I can look at what is changing with the thing I'm looking at. I can focus on the change, the growth, or the decay. That's why exponential models are really useful for that. They strip things down to their base. All puns intended. And that's what I'm going to focus on next between these two. Well, base 2 is something I do not have on my calculator. So I'm going to say, you know what? I'm going to make a capital G for growth model. And I'm going to take it times some, whatever my initial amount, as E to K times T. What I'm going to do is I'm going to hold all of the special magic into K. K is going to become a constant. That includes the time rate. So I'm going to make K hold all the information for me. And this is what most mathematical models do. Instead of using a different base for everything, when we first learn it, we'll say, I've got cells and they're doubling, so I'll take 2 to some power. But at the end of it all, we'll end up using E to some constant times T. In fact, I can say this for both growth and decay, and all I have to do is add, if K is positive, it's a growth model. And if K is negative, it's a decay model. So I've taken what the book lays out is about 12 different equations for different models, and we can break them into one pattern that gets repeated depending on how the thing we're looking at changes. So our only problem then becomes finding K. And that's not too bad. Before I came to the Mount, I went to Southern Vermont College, and one of the big groups of cohorts they taught was business people and people in the biological sciences, specifically going into rad tech. So I did a lot of focus on radioactive decay. I also did population and biological growth. So I'm going to look at a couple examples of this growth and decay model, but we're going to use these rules of algebra so that we only need to remember one thing, this. We only need to remember this. And we're going to use the type of problem to figure out K for us. All right, so I'm going to do a population growth. So let me change colors here because that yellow was hurting my eyes. So we're going to look at a population growth. And I have a town that its population, I think I'm going to use P for population. P is a good variable for population. Initially is 16,400 people. Now, you might have seen me, I did this in the other class using the base 2 model. But I want to show you how we can make this work for solving for K, and so that K becomes our driver, and then we only have one formula to remember. We could know, let me get my times here, that this population doubles every 30 years. All right. Actually, you can go to the CIA World Fact Book, a couple of different demographic statistic books. There's a Data World, which keeps statistics. And the projected doubling times of populations or decay times of populations, like where I live in Vermont right now, Vermont is losing population. More people are leaving the state than being born in it or moving into it. And then so there's decay rate models for parts of the state. Where in other areas they have the growth rate due to birth cycles. This is actually a very important part of public planning. And as you've seen, our infrastructure has suffered a blow due to the change in trade cycles and activity of people. Our infrastructure is really dependent on where people are, and delivering resources has limits. And so if your area is growing and you know the rate of growing, public planning, you should have an idea of how often you need to add resource to it. So we know that every 30 years it doubles. So I can make a population model that my population as a function of time is my initial population times an exponential, and I'm going to give that k constant there, that k constant. You'll see in different books, sometimes they'll make it, you'll see a lambda or a tau, depending on which science is going. Tau is the Greek letter for t, and so it's sometimes called the time constant. Lambda gets used in radioactive ones. It's usually divide by lambda. They all have a meaning within the field. Because I'm talking about generic versions, I'll use k, oddly enough, for constant. And k, you'll sometimes see books, because of how it transitioned in, as the Greek kappa, which looks almost like a K. It has a little hook on the bottom. And kappa and constant came together from Greek, and then it fell into English as a K. And so I'll go, I'll use K for constant, and people go, oh, you can't spell. It's like, yeah, I do maths, right? It's all Greek to me. And so this is our base model. And this will work for any exponential growth or decay. We start there. What we want to do here is, first I want to build my model with my given information. And then usually the questions will say, if the what will be the population in 50 years, right? So what is the population in 50 years? So we know it doubles every 30 years, and we want to know what it'll be in 50 years. So before I even calculate, I just think, well, if I double 16,400, that would be 32,800. So my answer is going to be bigger than that. Now, if it were to double twice, that would be 60 years, which is a little bit further than my 50, right? 60 is bigger than 30. So 2 times population. This is just something I'm doing in my head to kind of set boundaries. 2 times, it would double if I double once, right? 2 times this is 32,800. If I double one more time, it's 65,600, right? If I double this. So this would be in 60 years, and this would be in 30 years. And what I'm looking for is in 50 years, so it's going to be somewhere around there. I just want to think about my problem before I dive in and start using all these exponentials. I want an idea of what's going to happen. If the population doubles every 30 years, in 30 years it'll be 32,800. In 60 years it'll be 65,600. Well, I'm looking for 50 years, so I'm somewhere in the middle of that. And I'm just going to use that as my guiding. Now I'm going to let the math tell me what to do. Well, if I double, so P at the doubling time is equal to 2 times P naught. I'm not going to put in my 16,400. I've watched a lot of students, they'll rush right in, they'll say, hey, at the doubling time, this is 16,400. They'll get a number, and then they'll do all these calculations on the number. I'm going to make it, I'm going to say, hey, I double what I originally have. So, I'm going to substitute all of that into the model I want. And what was my doubling time? It was 30 years. Here's the joy of this. Look what I have on both sides of the equation here. So I'm going to divide both sides by original population. This is a key to exponential models. If you measure the time it takes for something to double, something to have, doesn't matter how much stuff you start with, you're looking for half that. And the dirty secret about these exponentials is they're percentage generators. If k is positive, this generates things from the number 1 to infinity. We can think of 1 as equivalent to 100% of the stuff. And 2 would be 200%, right? Doubling is you have 200% of something. I kind of think of these as percentage generators. Because if k is negative, then my half-life is when I get 0.5. And so these things spit out multipliers. Their job is to spit out multipliers of whatever's in front of them. So if you're looking for doubling, you're looking for this to spit out the number 2. You don't care what's going to sit in front of it eventually. You just want to know when this spits out the number 2. So this simplifies nicely to 2 equals e to the k, with whatever my doubling time was. And most of the time I start my problem right here. But I would get in the habit of substituting in, making sure you're comfortable with the initial amount canceling, and that you can solve for k now. Well, how do I solve for k? K is trapped upstairs. Well, k is trapped upstairs. I have some base, and k is upstairs. If I take the natural logarithm of the base I have, I'm going to get my upstairs out nice and clear. So I said these are special. These inverses are special. They're the secret sauce. This is weird. I have my over there is where I can see if this camera is working. And so I point to this, and I look over there, which puts my head off the screen. I think most of the time you've seen me doing this. I should be doing this. I should be talking to you. So, this base that we have in our variables in the power, to get rid of it, I'm going to take the log. I'm going to take the log. See, not over there. There. Yeah, I'm going to mess this up. I'm going to take the log of whatever the base is, and they will cancel, leaving me what's upstairs. And that will let me focus on bringing the upstairs down. And so that's why I called it the secret sauce. So let's do that. So we'll take the natural log of both sides, because we can do that. Well, the natural log of something to the base of the natural log cancels, and I get k times 30 equals the natural log of 2. The natural log of 2 is a number. It's actually a number that pops up a lot. That's why I quoted it as 0.69. All right, and so k is equal to the natural log of 2 divided by 30. I now have my k constant. Sometimes, depending on the problem I'm doing, I leave it like this. This can be messy to do, so I will approximate it to a decimal. Now here's the secret. When doing things like this, keep a large quantity of decimal places. I think I tend to try to keep 3 to 4 significant figures, so things that aren't zeros. So natural log of 2 divided by 30 is 0.0231. There's 3 sig figs. I'm going to take 0.5, so I've got 5 sig figs for right now. That gives me enough room that I won't get weird rounding errors in the future, right? This 0 in front isn't significant. It's just holding place. These numbers are the significant ones. I took 5 sig figs. General rule of thumb, take 2 more than you need. And you'll find that most applications require you to take 3 or 4 sig figs. So I picked 5. I'm just trying to avoid rounding errors. All right, so I have now built what I need to build my model. So I'm going to come back here. I'm going to get the super glue out because that's what we do with models. And so my population at any time is my initial population times E to the 0.023105 times how much time has passed. I have made an exponential model that works for the growth. And in this case, we said, hey, how much is it going to have in 50 years? So I'm going to drop 50 in there. And what did we have? We started out with 16,400. So E to the 0.023105 times 50. And so on my calculator, 16400 times second ln gives me the E key, 0.023105 times 50. And that gave me 52,000. And I'll round up 67. Notice the double check I did when I was looking at this. I said, hey, it's got to be somewhere in between. It's got to be between 32,800 and 65,600. Closer to the 65,000 side because of how doubling worked. That was just my mental check on it. If I come down here, yeah, my number was good. So our model works. What's nice about this type of modeling, yeah, finding that K constant can be a pain, but it means you will only ever need to use one key on the calculator. You only ever need to type in one thing in your spreadsheet. The only thing you keep track of is K. Everything else will always look the same. Be it you're looking at radiation decaying, you're looking at a population growing, you're looking at, you can now, go work for public planning and you can do the population model for Athol versus Gardner versus Leominster. I'm not from around here. I'm sorry, don't hate me. Worcester, right? And you can look at the different population models and all you have to do is change K. You keep your K changed in there, you've got one little equation on your spreadsheet, and you now have a tool that will take care of whatever you're modeling. Exponentials are very powerful functions. They're used in a lot of different places, and it's easy to say, okay, I'm going to use doubling, so I'll use base 2. I have a tripling time, I'll use base 3. But it's much more efficient to just turn everything into base E. All right, I'm gonna do a radioactive decay because they're fun, and I'm gonna do phosphorus 32, and I hope we'll appreciate a small thing changes here, and that's the sign. Oh, I have room. Ooh, this is gonna be close on room. I'm gonna clean off the blackboard. Give me a second here. While I clean off the blackboard, I'll let you see the rules. Stare at the rules while I clean the blackboard. Blackboard cleaning commencing. Look at those rules. Aren't they pretty rules? They're very useful rules. Blackboard cleaning is still commencing. Blackboard is cleaned. No more rules. Oh wait, did I switch that back? Oh, I didn't. Here, you need to stare at the rules a little bit more. Look at those good rules. Aren't those great rules? Yeah. Back to our blackboard. Alright, let's go up here. Oops. Ah! No! We don't want yellow. We're not those type of people. That would hurt our eyes. I have to scroll up to the top. I'm way down on the bottom. There we go. All right, so we're going to look at radioactive decay. So what happens is a chunk of substance, and in this case it's going to be made of phosphorus-32. Now phosphorus-32, inside the nucleus, the protons and the neutrons, let's see, I guess I'll use colors for those. We'll make protons blue. I've always seen them as blue. I don't know why. And neutrons I'll color in yellow. Are packed tightly in the atom. And there's more than 3, but I'm not going to stand here and draw all of phosphorus out. But it's bound by a nuclear force. Nuclear force that binds us together. Because the protons are the same charge, they're pushing on each other, they're pushing away. Those neutrons actually help them pack a little bit better by getting in between them. They kind of fill out. And this nuclear force that holds this together is kind of like a rubber band. And so these are pushing out, stretching on it. And all atoms are like this. All atoms, the nucleus of the atom, internal charges are pushing it apart, with the nuclear forces holding it together. And occasionally, the nuclear force gives way, and this atom breaks apart. And the rubber band will snap, and then it'll glue back together on other parts, and this will break down. And this phosphorus breaks down into sulfur. And a beta particle. So the atom changes into another atom. This happens for everything in the universe. Everything in the universe is decaying, right? And working its way back down to basic particles. The processes that had to pack all these protons together, it needed to happen inside of the early conditions of the Big Bang, or inside the center of stars, crushing down these great forces tying these things together. Well, now that these atoms are free from these forces, they want to go back to just kind of being further apart, and so they break down eventually. And so every time this breaks down, this substance loses some of its phosphorus. And so radioactive decay, eventually, I only have half the phosphorus in there. Some half-life passes, and the amount of phosphorus has halved away. And so we, as a society, we use this process. We use these different processes. Again, I taught a lot of rad tech, radiological technicians. They would find different substances for you to imbibe. This breakdown releases particles and radiation. The radiation you could see. And so if you could imbibe this, the radiation would emit from where this stuff was inside of you. Helps you see inside of you, basically. But you want to do it in a way that isn't damaging and doesn't last too long. So you look for substances that have half-lives that are short. Now, phosphorus-32 has a half-life of 14 days. And that says if I start with an amount of phosphorus-32, 14 days later, I will have half of it. Notice my sentences now. We should be thinking, wow, this sounds like an exponential. This sounds like I can take my amount of substance as a function of time, start with my initial amount, and do this. Because I'm talking after a certain amount of time, I have half. And these are percentage generators. And this is going to generate a half for me. Well, for me, what I need to know is K is going to be less than 0 in this case, for it to be decay. Now, I'm not going to force that. I'm going to watch it fall out of the equations for me. But the stuff is starting to decay. It's starting to decay. Well, what I have is at 14 days, A is equal to 1/2 A naught. That's good. So let's do something here. Let's jump right here. At 14 days, 1/2 A naught is equal to my initial amount times e to the k 14 days. Now notice we're measuring time in days. Some substances, like if you do radioactive carbon dating to figure the age of something, you measure the half-life in years. It all depends on what you're looking at. Well, those are going to cancel each other out. And I'm going to, just for convention's sake, I'm going to write the 14 in front. We want to find what the K is for our phosphorus. Now, this is again in my exponential. And my exponential has a natural, the base of a natural log. So I'm going to keep pointing to this, and hopefully I'll get my camera steering technique right. I have e to some power. If I want that power to come down, because my variable is in that power, oops, I'm doing a bad weatherman now, right? If I want that to come down, I have to take the log of the base that I have. So I want natural log in front of here. It's going to let me get my variables free! Yay. I know when you signed up you didn't realize I was this crazy. I didn't realize that I was this crazy when you signed up. I didn't know you were signing up. Alright, so I'm going to take the natural log of both sides. ln of 1/2 equals ln of e to the 14 times k. But these are going to cancel. They invert each other. Go away! 14k. Now, in a calculator world, it's really, really nice. Our calculator is going to spit out a number for this. But I want to show something. I said k has to be less than 0. But I wasn't going to do anything to enforce that. And here's why. Remember, this is the ln of 2 to the negative 1. And the negative 1 can come out front. And I'll divide both sides by 14. So I get the negative natural log of 2 divided by 14. Notice how that natural log of 2 keeps popping up, the 0.619. And there's where my negative sign came from. And so I'll do this on my calculator. Now granted, I could do the natural log of 1/2 divided by 14. I'm going to get the same thing. And I get a k value of negative 0.049511. So I have built my model. And my model in this case is my amount of substance at a given time is my initial amount of substance, E to the negative 0.049511 times T. And I have a decay model because I have a negative sign up front. Sorry, you can't see me pointing at my computer screen. I know this is a decay. This is decay. Look at that. I have watched a population of a town grow. I have watched an atom break apart into other atoms with one equation. And the only difference between the breaking apart and the population growing is the sign. All of the magic gets held in the K constant. The K constant controls the rates on everything moving through. All right. Now, Bankers. We gotta love bankers. They helped invent E for us. They had a compound interest rate. So the amount of money I have in my bank is equal to the principal I deposit times 1 plus the interest rate divided by the number of times I compound my interest rate to the NT. And so A is my money, is amount of money P is the principal, which is the deposited amount, which is the amount interest is applied on. R is the rate. Normally you'll see this as 6%, but we'll write, or whatever the number is, I'm using 6%. For some reason when I think of credit rates, I always think of 6%. I think when I was first learning this stuff, this was a common interest rate. I think now savings is less than 1%. I remember as a kid, you could save between like 3 and 5, and loans were low. Now loans are what, 15-20% sometimes. Our loans are really low too. I use 6% all the way up to 15 or 20 with like credit cards and weird things. It's always odd at how far the savings has changed. And so as a kid, you used to be able to actually make interest putting money in your bank. Now you don't. But we'll write the percentage as a decimal. N is the number of times it's compounded. So if they take the interest on your money and put it in once a year, it's N equals 1 is yearly. N equals 12 is monthly. N equals 12 is monthly, 52 is weekly, 365 is daily. Right, and you can keep going per hour, per second. And what bankers did is they said, well, what happens if I'm constantly putting the money back in, right? Or applying the interest. And what they found was that this 1 over R divided by N to the NT approaches this thing called E. And so this whole thing has what we call continuous interest rate formula. And that's your amount in the bank is equal to your principal E to your rate times time. It's an exponential function. Your rate is determining how often you're approaching your amount, and it processes your time, so to speak. And this high level financial transactions tend to use that. Definitely you tend to get this applied against you more because this makes money more quickly than compounding on other time periods. But this is becoming more of a common way. And it's actually how we discovered the properties of E was through banking. Banking in, I think, the 1600s. This question came about, and Euler kind of figured out what would happen if we kept approaching interest over and over again. And so you'll see for continuous interest problems, you want to use this formula. For anything that is compounded, you want to use this formula. And the trick is compounded, be it monthly, weekly, daily. I tried to avoid signing these, but some of the random questions will ask you compounded monthly versus compounded continuously. They'll do a comparison between the two. It's not a bad thing to do. Notice though, nothing new, right? We have an exponential times some original amount, we get another amount back out. And the only thing we need to focus on is the rate. And that's the power of exponentials. Okay. Look at the problem for that in the homework. The example in the book is good. There's one other model I want to show that exponentials get used for. And this is kind of neat. This actually falls from a set of differential equations called a logistic model, where the exponential answers come out. I'm going to draw a strange graph here for a second. And I'm going to put a blue line in the middle. All right, so this is a graph. And this is time going across this axis. So we have some starting time, we'll say time 0, and we go off into the future. And this is a population. Some population, which will be a function of time. This blue line is called, we're going to represent as C, and it's the carrying capacity. Now what happens in environment is you actually have two competing factors. You have the factor of procreation, the population doubling time. The animals in the environment are trying, and we'll say this is salmon. This is salmon in a fish farm, and so the salmon make more salmon. Right? Basic biology. Well, what do species do? You need food, water, shelter, propagation of species, right? And so they propagate, and that's an exponential model. And so starting here, there's generally an exponential curve going up of population. If I start with some population, it will want to double and it'll make an exponential curve. But nothing is immortal. The salmon are dying. Natural consequences. Also, the environment they are in can only feed so many of them. And it's actually a very complex, the food sources and the ability to process their waste. Right? If you have a salmon in a salmon farm, their waste will lead up to a certain part, disease proportions go through. So they can't populate completely, right? Or infinitely. There's a limiting factor that causes a decay model. And those two models come together for what's called the logistic curve. And it tends to look like this. You have some starting, it wants to propagate, but as more and more fish get into the stream, they use up more and more resources, which increases the decay rate until the decay rate and the growth rate balance. The rate the fish are dying is equal to the rate the fish are being born. And so the population doesn't change. And that's called the carrying capacity. That's how much fish this environment can handle in equilibrium. Well, you can try to introduce more fish to your salmon farm, but they're going to die off until they hit that carrying capacity. And so these competing exponentials end up making a model called the logistic curve. And they come out of predator-prey relationships. Growth and decay models. They pop in environmental science a lot. In fact, most of the logistic curves that I look at generally deal with environmental capacity, because what happens is this carrying capacity is the ability for the land to feed a species, and the carrying capacity shifts based on land usage and environmental factors. And so these logistic curves that pop out of that, well, they end up having a solution. And so the population at any given time, at most, will be that carrying capacity, whatever the environment can handle, divided by an exponential. Notice this is a negative exponential, so as time goes on, if time were to go out to infinity, this would get close to 0, and this would reach the carrying capacity. And so the constant A and B will determine, the constants A and B will determine how quickly that happens, and how that relates to the carrying capacity. And so you can solve for A at time equals 0. So it's based off of your initial population. And then B holds the rate, just like K did. All right, I'm actually going to pick up with the logistic curve on Thursday. And that's going to be our last lecture. What will be these models that come out of exponential functions. I really noticed I've switched over. We've done the basics of the algebra. This, in class-wise, I would have said, hey, here's the homework on the algebra of logarithms and the algebra of exponentials. You have that in your homework assignment. I handed out a half-decent chunk of putting logarithms together and expanding them to get practice for it. Please try to look at your homework. I know the due dates are scheduled for the end of everything, and I also know not everyone's listening as I do these. Some people are playing catch-up or whatnot. But we're going to look at particular models on Thursday and kind of tie it all together to come through. And I'll pick up with the logistic curve. We're getting close to 12 here, and I don't like pushing a large chunk of time for digesting. So I think I'll do a little bit more about the banking equation and a little more about the logistic curve once we pull back out of that. All right, be well.